So welcome back to the session on the fossils and fossil dating. So here we were discussing on different types of fossils and we almost completed the casts and modes. So we saw that there are three types of fossils: the actual organic remains, that is the complete body or the parts of the body; then petrified fossils, wherein the different parts of the body get replaced by different types of minerals step by step; and then casts and molds. So we were discussing on casts and molds. So we saw that a mold is an impression of some hard parts, um, which in course of time gets hardened to become a rock. Okay. Later on, the organism decays, that is, the soft parts of the organism decays, and the organic material gets removed by percolating acidified water, and a cavity or a pit of depression is formed that shows the external configurations and surface markings of the original material. So that is known as the external mold. I hope you remember that um, the cast, it is formed when the surrounding material it gets hardened, and this surrounding material it even keeps or maintains the or retains the surface marking of the original organism. Okay. Uh, and sometimes the internal cavity of the body, that is the shell and all, is gets filled with mud or sediment or mineral deposits before the shell is dissolved by the action of percolating water. In such cases, these molds are known as internal molds. I hope we have already seen the figure here, isn't it? So this is not the actual shell, but because of the percolation of what you call the minerals or like intrusion of minerals or soil particles from the surrounding medium into the shell. So there was a shell inside this particular a shell was buried here, and the space inside or the cavity inside the shell it got filled with the soil particles, and slowly because of the reaction of the percolative acidified water, what happened is the shell it got completely decomposed. Okay, but the soil particles which got inside, it got hardened, and it was retained as a uh, the internal structure of the shell. Okay, so this also can be taken as a fossil because it is showing the internal characteristic features of the shell, even though it is not showing the retaining the actual shell or the actual organism, but it do provide the impression of the internal shape and the structure of the shell. So this is what is referred as a mold. Here you can see it is not the actual organism, but it is actually the external environment which has retained the impression of the outer surface of the shell. So here again you can we can get an impression about or a picture about the actual shell that was there in the particular medium. Okay, I hope it is a rock. Okay, it has got solidified into a rock. So this also provides an impression. Okay, so this is again what is referred as a mold. Okay, then we have if the mold, yeah, these molds represent internal molds represent the internal structure of the shell and the exact shape of the animal. The molds are available largely for molluscan shells, foraminiferans, and radiolarians. Okay. Then we have if the mold showing external form is gets filled with mineral matter later, natural cast of the original object is produced, which reflects only its external form. So, natural molds and casts form a very large proportion of the fossils that are found in sandstones and limestones. For the preparation of artificial casts, uh, obviously this is a natural cast. Okay, here you can see this is a natural cast, right? So, for the preparation of artificial casts, we can use like rubber solution or melted wax or plaster of Paris, which is made to fill the external mold, and natural molds of several men and dogs whose artificial casts have been produced by plaster of Paris have been found in the ancient ash-covered town of city of Pompeii, where they were mass buried by the eruption of the Mount Vesuvius. Okay. Now we have the next type of fossil, that is the tracks, trails, and burrows. Okay, sorry, coprolites and gastrolith. Okay, so gastrolith they are hard stony pieces found from stomachs of ancient reptiles and fishes, while coprolites They are fossilized fecal matter of ancient animals. So their study provides valuable information about the food and feeding habits of fossil forms to whom the fecal matter belongs to. So the excretory matter of certain animals, these reveal the shape of the intestine. For example, spiral valve of the shark. Okay, so this fossil excrement may sometimes reveal the shape of the intestine or give a clue as to the kind of food digested or the feeding habits, etc. Okay, so that is about the coprolite and gastrolite. Then we have the tracks, trails, and burrows produced by certain animals because they provide a clue to the general nature of the animals. Tracks are footprints left by animals on wet sand and mud, while they have been preserved by sedimentation and hardening. Trails are a series of marks produced on soft sediments by crawling worms and snails or dragging of tentacles by the coelenterate. Some burrows and tubes left by extinct animals provide some evidences of their existence in the past. Um, some such fossils you can see fossils of footprints are common for dinosaur reptiles from Triassic rocks of Connecticut Valley in USA. Similarly, the tracks of Mississippian amphibians form another example for tracks. Okay. Uh, and there are such plenty of examples from the tracks trails. The trails you can see that we can have the impression of fins of fish, then on like soft mud, then markings of movements of crustaceans or urchins, etc. They form the these what you call the tracks and trails. Regarding burrows and borings, uh, fossil burrows provide information regarding the behavior of the resident animals over there. Okay. So these are the different types of fossils. Now, this we have already seen in the previous presentation, and this is just a summary of all those structures, all those different types of fossils. This is the complete specimen preserved in the amber. Then recrystallization here. You have the carbonization. This is actually the parts of a plant. Okay. Then here this is the impression or the left behind on rocks. Then again human footprint under the tracks, trails, and the burrows. Okay, here you can see the replacement. The complete ammonite had been got replaced by iron pyrites. Okay, so this is actually an example for pyritized type of petrified fossil. Okay, now we can go to the fossil dating. So what are fossil dating? Okay. Now the fossils actually why what is a fossil dating? Fossil dating is actually the dating of fossils, or what we can say as finding out the actual age of the fossils. Okay, how we can do it? Uh, there are two main types, that is relative dating and what you call the absolute dating. Here you can see. So relative dating is where we just know when if we have two fossils, okay, or if we have data on two different fossils, we can say that okay, the fossil A was actually earlier to fossil B, or it was later to fossil B. So somewhat like that, relative time zone can be calculated by way of relative dating. But absolute dating is not like that. We get the actual age of the fossil. Okay, okay, these many years before. Exactly. Okay, you needn't have a what you call comparable data from another fossil for that purpose. Okay. Now, relative dating, here you can see there are two kinds, that is stratigraphy and biostratigraphy. Stratigraphy, if a fossil is found between two layers of rocks whose ages are known. So we know the ages of the two layers of rocks. Okay, so the fossil's age is thought to be between these two known ages. I hope you got it. Okay, we have a we have excavated a particular area, a land, okay, and we have found a fossil from two layers of rocks, and we know the ages of those two layers of rocks, and we estimate that the age of the fossil will be between those two known ages, or the ages of two rocks. Okay. Because rock sequences are not continuous, but may be broken up by fault means a crack or crevice, okay, or periods of erosion, it is difficult to match up rock beds that are not directly adjacent. So here what happens is we can just estimate the age. It needn't be accurate. Okay, so that is known as a stratigraphy. Strata means layers. Okay, here the layer refers to the layers of rocks. Okay, graphy means obviously mathematical induction. Right? So here we estimate the age of fossil with respect to the position of the fossil between two layers of rocks whose ages are known. Fine. Now, biostratigraphy, fossils of species that survive for a relatively short time can be used to match the isolated rocks. Okay, here we have uh, like we know, for example, dinosaurs were found only during the Jurassic period. Okay, so if we are getting fossils of dinosaurs, obviously we can see that that particular rock strata is from the Jurassic period. Okay, so such kind of a estimation of time is known as the biostratigraphy. So these two methods are actually the relative dating. Uh, Here we get the idea of about the age of the fossil with respect to where they are located. Okay, it needn't be accurate, but still, this is for evolutionary purpose for studying evolution. This is also this also provides sufficient amount of data. Now, the absolute dating, okay, mainly it is through the radiometric dating. Radiometric dating is actually uh, um, used in geochronology to establish the geological time scale. That is, we are actually finding out the fossils. But what is happening here, or what do we do? So it is actually using radioactive uh, like elements. Okay, radiometric dating is usually by way of using radioactive elements. Okay, so the here what happens is the rates at which I hope you have studied in your chemistry classes that the radioactive elements they give off the radiations and by way of which they start to decay, isn't it? So and each of the radioactive element has a half-life period. Okay, T half. You may have studied it. Okay, so here what happens is the rates at which various radioactive elements decay they are already known. Okay, that is half-life period. We already know whether it is uranium, whether it is carbon, whether it is potassium, radioactive potassium or radioactive calcium. We know that T half. Okay, we know how much time it takes to decay. Okay, and the ratio of the radioactive element to its decay products. That is, if it is carbon, the carbon 14 is the radioactive element, and we know the T half life of the half life of the carbon 14, and what is the product. Okay, so the ratio of the radioactive element, for example, carbon 14, and its decay products. So what is produced by the decay of carbon 14, that product. The ratio it shows how long the radioactive element has existed in the rock. What does it mean is, like, for example, if we are getting an object, okay, and if we know that it contained carbon compounds and it contained carbon 14 in the past. Okay, what we are going to do is we are going to measure the carbon 14 present in the particular object. Okay, present, how much it is present at the like now, fine. And then what we do is we also measure how much amount of the product, the decay product is present in the particular object. Then we find the ratio. Okay, and this particular ratio it will give the how much time the particular object has been there in the substrata. Okay. So this ratio of the radioactive element to its decay products show how long the active element had existed in the rock, and this rate it is the time it takes for half of a sample to decay. We will see two examples here. One is radioactive carbon dating, another is potassium argon dating. Okay, so it is already known that T half or the half life of carbon 14 it is 5,730 years. Okay, so carbon dating is only relevant for dating fossils less than 60,000 years old. Okay, so what happens is carbon 14 uh, if it is present in a particular object, it decays to its half the amount by 5,730 years. So we can use carbon 14 for dating only an object of 60,000 years old. Radioactive elements are common only in rocks with volcanic origin, and so the only fossil bearing rocks that can be dated radiometrically are volcanic ash layers. So here we use it to estimate the age of organic materials. Okay. Similarly, with respect